So now we'll talk about the model 16. We'll talk about the imbalanced dataset for classification, and we will know the remedy behind this classification which has imbalanced dataset. So how do we define the imbalanced classification dataset or skewed dataset for binary problems? So let's say the sample results are highly biased. Let's say there are 1000 samples and 900 are ones and 100 are remaining. So majority and minority are there. So if you use any metrics, precision, recall, F1, the confusion matrix, it will not give us a proper insight because the datasets are highly biased or the output results are highly biased. So how do we handle it? How do we handle the imbalanced data? So there are four methods. One is the random undersampling, random oversampling, hybrid method, SMOTE method. Okay. Random undersampling is nothing but if you have such a dataset, what's the zeros, 90%, 10%, what we do is we reduce the majority class samples to the number of minority class. We just take 100 samples from the majority and 100 from the minority. So we can do this to make 50-50 sharing, because in any random observation the output should be of equal proportion. Okay, to do that we can just do undersampling, but the problem is that too much information loss, because we are losing too much information from the majority class. The remedy is ensemble learning, in which we are using different tree models with different data sets. Let's say adapters, so we can do that so that no majority data set is missed out. Other one is rows, random oversampling of examples. So what happens is that in this case the minority class will be taken multiple times. Let's say 900 samples from the majority, same way 900 samples from the minority also to equalize it. But this case it is overfitting because we are using the same sample again and again. So how much, let's say only 3 data sets are there, but you are using the 3 samples again and again many times, it is overfitting. That means you are taking too less data to generalize the whole data set. So for this, famously we use regularization to reduce the overfitting, that is L192. Okay, there is a hybrid method, which uses both the things. We can use both oversampling and undersampling both in the ensemble algorithm. Okay, ensemble learning, we use it. There is a fourth method called SMOTE, which is synthetic minority oversampling technique. What happens is that we just plot the output class 0 or x or triangle. What we do is artificially generate minority class data set. Let's say this whole complete dark triangles are the original data set. So what we do is artificially generate another data set in between the distance. So like this. So we can just using this method we can just generate more minority classes. But the problem is that it creates noise. Noise is nothing but overlap of data. Let's say a class of data is already there. You are creating another data over it. So this kind of creates an overlap and creates error. So the remedy is to do it in a controlled manner or just in a reduced form. Okay. So we will just implement these remedies in the coding part. So let's make a classification dataset from 10,000 data and 2 classes, and the weightage is given. That is we are screwing up the dataset 90%, 10%, 90% will be zeros. So just when we calculate the label distribution, so you can know that 9,000 is 0 class and other 1,000 is 1. So same way we can use the counter from the collections to know how many of them are there. Okay. So here example is that. So first time we are going to use random sampling. So most collection algorithm will only perform optimally when the number of samples of each class is roughly the same. Highly skewed data sets where the minority is highly outnumbered by one or more classes have proven to be challenged while at the same time becoming more and more common. Typically, the minority class is the one on which the prediction are most important. One way of addressing this issue is by resampling the dataset as to offset this imbalance with the hope of arriving at a more robust and a fair decision boundary than you would otherwise. Two main approaches to randomly sampling an unbalanced dataset are to delete these examples from the majority class called undersampling and to duplicate the examples from the minority class called oversampling. Random and oversampling duplicates the examples from the minority class in the training dataset and can result in overfitting for some models. Random undersampling deletes the examples from the majority class and can result in losing information invaluable to the model. So let's import the random oversampler from the imblearn package dot oversampling. So the oversampling, random oversampler sampling strategy minority. What happens is that it means that the majority, if it had 1000 examples, the minority has 100. The strategy will oversample the minority to 1000. And if you use this strategy as 0.5, it would ensure that minority class was oversampled to half the number of the example of the majority class for the binary classification problem. This means that if there's a 1000 majority example or 100 minority, the transformed data set will have 500 samples from the minority class. So this way the overfitting is reduced. The same thing we use is we just take 0.8 here. That means 80 for 1000 examples, 1000 majority examples, we will have 800 minority dataset. So same way we will just fit this sample xy and we get oversampled xy. We just know that y is 9000 and 9000 and here 1000. And for after fitting this model, we just know there are 9001 and 7200 ones. So oversampling has happened. So let's compute the precision. So using the decision tree model, and which uses stratified k-fold, and sometimes repeated stratified k-fold also used for the splitting the dataset. What happens is that if the ratio between the zeros and ones are not equal, so in the splitting case also the training and test data set can become 0 0 or highly skewed up. So we don't want that. So in every time we create a fold of data set, 10 number fold, what is it? The ratio should be maintained. The ratio of zeros and 1 should be maintained. For that we are using a stratified k-fold, and the advanced version is called a repeated stratified k-fold. So we will use this both thing for the cross validation. So model XY scoring is precision and CV is split from the stratified k-fold. And end job is nothing but it is a approach to increase the computation efficiency. So if we take the mean value, it is 83%. That is 83%. It is able to properly classify using the decision tree classifier. Okay, for the original data set, let's say for oversample data set, the accuracy is increasing to 97%. That means this approach is working properly. Okay, so let's do the undersampling, in which we give majority. That means the 100 sample will be transformed. The 1000 example in the majority and the 100 example in the minority will be undersampled. In the minority will be undersampled such that both class have 100. Okay, in this case the 100 samples will be decreased. So what we do is a sampling strategy 95% same undersampler. So previously we had 9000 and 1000, and in this case the majority sample is reduced to 1051 here. That is 95% it is reduced. Okay. So once we do that, let's compare the precision. For the original dataset, it is 84% as we know it earlier. For the undersampled, it is 92%. It's still higher, so it's good. So what we can do is we can just create a hybrid of this using the pipeline. So what the pipeline means that we just defined what is over. So just give the values here, and we put a step into the steps or in the list, which happens that it creates the prediction for oversampling and then undersampling using this decision tree. So we just put these steps inside the pipeline, which is imported from the imblearn.pipeline, and then we find the cross validation score using the pipeline. So instead of the model, we just put the pipeline here. Okay, so in this case we are using repeated stratified k-fold. Instead splits, so 3 repeats are there and random is 1. So in this time, if we do, the mean score is 84%, which was basically It's almost same of this. The next method is SMOTE, synthetic minority oversampling techniques. So it synthesizes new examples from the existing examples. This type of data augmentation for the minority class and is referred to as synthetic minority oversampling technique, or SMOTE for short. SMOTE works for selecting the examples that are close in the feature space, drawing a line between the examples in the feature space and drawing a new sample at a point along the line. Specifically, a random example from the minority class is first chosen, then the key of the nearest neighbors for that examples are found, typically key equal to 5. A randomly selected neighbor is chosen and a synthetic example is created at a random selected point between the two examples in feature space. This procedure can be used to create many synthetic examples for the minority class as are required. The author of the SMOTE paper suggests that first using the random undersampling to trim the number of examples in the majority class, then use SMOTE to oversample the minority class to balance the class distribution. The combination of SMOTE as well as undersampling performs better than the plain undersampling. The approach is effective because new synthetic examples from the minority class are created that are plausible, that is, are relatively close to the feature samples to existing examples from the minority classes. A general downside of this approach is that the synthetic examples are created without considering the majority class, possibly resulting in ambiguous examples if there is a strong overlap for the classes. So what we do is just plot the uh, scatter plot for the particular class. So as we know from the dataset Y, just know the counters here. So counter item 0 or 1 for that particular label, pair Y equal to the label, the 0, just take the row I, so x of I and x of uh, that value, x or y value, then just we plot it. So these are the data distribution. So this is 90% of zeros, 10% of the ones are here. So now we are going to, it is not. So before we had 9,000 and after that we are almost having same values. So this is oversampling. So this SMOTE is basically imported from imblearn.oversampling. So now after fitting this sample, this SMOTE oversample outfit, we get x over and y over. So we are going to plot it again inside here in y over and x over y over. We just plot. We just know that it's almost equal, as we know that sampling are equal. So from here to here, it has happened. So both have equal zeros and ones are here. So we will explore testing different ratios of the minority class and majority class, obviously. So we can increase the k values, k nearest values to 1 to 7, something like that in the pipeline stuff. So same way in the pipeline, the k neighbors which were from k1 to 7 can be done. So just we have to take these data samples here, and then number of classes is class 1 and 98% weightage. Okay. So there are k values for k values for division tree. We are just specifying the k, and we are creating a pipeline over under than the SMOTE. Sorry, over for over we are using the SMOTE, and then we are going to use the undersampling and we use the division tree model in the pipeline. And then we use this cross validation score for the key mean value for given k. What is the ROC mean value? So what is the ROC mean value? So from this, unless we can just know that for k equal to 5, we get the 85% ROC value. Okay. So there are many popular variants of SMOTE, borderline SMOTE adaptive or adaptive synthetic sampling, etc. So this is how we um, balance the unbalanced dataset. Thank you.